in the last lesson, we learned how to draw a Lewis structure. And we have to start with a Lewis structure for all of these next few lessons. You have to be able to draw the Lewis structure to be able to do the rest of what we're about to do. So a resonance structure is when you have a Lewis structure can be drawn in multiple ways. This usually happens when you have some double bonds off the central atom and some single bonds off the central atom. Because we don't know which way it's going to be in actuality, like in nature, we don't know which way it's going to bond. We show it in all the possible ways. So a double-headed arrow shown between each of them tells me that those are possible resonance structures. There's more than one way it could bond. We don't know for sure which way it is going to bond. Something tricky about resonance structures, and they're going to challenge you on this understanding, is in a resonance structure, all bonds are considered the same length because we don't know which side is going to be which bond. And so even though we know that a single bond is longer than a double bond, than a triple bond, in resonance, they're all considered equal because we don't know where that double or triple bond is going to go. So let's go ahead and start by doing a couple examples. In these examples, we are going to first draw the Lewis structure because you cannot determine resonance without having a Lewis structure. And so we need to, again, figure out our total number of electrons. So for oxygen, I have 6 for each oxygen, 6 valence electrons. But there are 3 oxygens in ozone, and so there's a total of 18 electrons I've got to do something with. Well, the only thing they can do is bond O to O to O, so that's what I'm going to start with. And so I'm going to have my oxygen is going to bond to an oxygen and bond to an oxygen. And when this happens, I have 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. So I have 18 electrons. And I have to be able to do some shifting around at this point. Now, in the last ones, it just worked out. So in the last examples that I did, if I go back to the previous examples, like for CO2, carbon was my central atom. These had your single bonds, and then it just worked out. We took one from here and one from here, made a double, and one from here and one from here made a double. So those just work out. Not all things are going to work out, and not all things are going to make perfect sense. So here's another way that we can optionally draw these, because right now I've just got 2 random electrons here, and right now my central atom is stable. So let me go through and erase all this stuff. And let me show you another option. If you get to one and it's sort of weird, what I recommend doing is doing just a skeleton structure and then filling from your peripheral or the outer elements inwards. So I'm just going to make a skeleton, just literally a skeleton. I know oxygen has to bond to oxygen, has to bond to oxygen. So I've used 4 of my electrons. So then I'm just going to fill from the outside in. So 2, 3, 4, 5, 6. Do the same thing over here. So I have 2, 4, 6, 8, 10, 12, 14, 16. Let's put the last one, 18. The electrons are in these weird bonds are not necessarily going to stay with the element it brings in with it. Electrons do some weird stuff with some chemical bonding, especially with these ones with resonance, and you just have to shift it around until everything is stable. So right now, both of my peripheral oxygens are stable, but my central atom is not. It's only got 2, 4, 6, and oxygen is not an exception. It must have 8. And so what I'm going to do is I'm just going to take 2 electrons from one of the oxygens and double bond it. So I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything is now stable, and let's make sure I used my 18. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So not all of your Lewis structures are going to be pretty. Some are going to be tricky. This is what we consider to have an option for a resonance structure. And so I'm going to redraw it down here so that I can show you how chemistry is going to expect you to show resonance. Okay. It told us that we needed to use a double-headed arrow. So in between these two, I'm just going to do a double-headed arrow. And then over here, I'm going to do the reciprocal or the mirror image of this. So instead, I'm going to put my single bond on the left and my double bond on the right. This is what we call resonance. We don't know which way it is going to bond in reality. We don't know if the double bond is going to be on the left atom or on the right atom. We don't know, so we just show all the options. And AP would expect you to show it this way. In resonance, though, big thing, all bonds are considered the same length. So even though this is a double and that's a single, we consider them to be the same length because we don't know which one is which in reality. So let's clear this page and do it again. So now we're going to do CO3 -2. So this is a little tricky because we haven't done a polyatomic ion Lewis structure yet. So let's just start with the CO3 and then figure out what that -2 means. So we have to figure out total number of electrons. So I have 6 for each oxygen. So I'm going to do 6 times 3 plus 4 for my carbon. -2 means it has gained 2 electrons, so it means plus 2 more electrons. So I've got a total of 24 electrons I've got to do something with. C is going to be my central atom, so I'm going to put it in the middle. Two, 4, 6. I'm going to fill from the outside in. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So by doing this, I've fulfilled all of the octets for oxygen, but carbon is not okay. So I am going to shift my electrons. So now I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and then I have 2, 4, 6, 8 around that. So I've used my 24 total electrons and everything is stable. Now, last thing we have to do, because it is a polyatomic ion, is we put these brackets around it and we say -2, because that tells that there were 2 extra electrons that appear, and this tells me it's a polyatomic ion. Then I have to show the resonance. This one is going to have 3 resonance structures. I'm just going to shift my double bond around the central atom for all my resonance structures. So in this one, my double bond's on the left. This one, my double bond's on the middle. This one's on the right. Again, I would need to put brackets around these. Having some space management issues. Because it is a polyatomic ion, we have to show those brackets. And then this would show the resonance that the double bond could be on the left, could be on the bottom, could be on the right. Again, when I draw these, I try to make it symmetrical. And so I typically do left, right, bottom, but you could have put something up here at the top, like this oxygen could be at the top instead of the bottom, as long as you have those 3 distinct sides. So this is what we call resonance. So let's answer a couple questions about these. Which of the following statements, if true, would support the claim that NO3- ion represented above has 3 resonance structures? So on these, we're going to look at our options. We're going to skip that question because that question really has to do with the shape in the next lesson. So we're just going to skip that question for right now. Let's look at this one. So it says the diagram above shows two resonance structures for the molecule of C6H6. The phenomenon shown in the diagram best supports which of the following claims about the bonding of C6H6. Okay, so first of all, let's talk about this weirdness. So carbon rings are very common in organic chemistry. AP does not expect you guys to understand organic chemistry. However, you are going to see organic molecules and you're going to see how they're drawn, you're going to see their names, but they don't expect you to completely understand that. Organic chemistry is a second year chemistry, and AP chemistry is from your first year chemistries, your 1010 and your 1020. And so on these, we can see that in these rings between the carbons, we have some double bonds and some single bonds, and they alternate. So single, double, single. This one's double, single, double. So showing that the resonance is within those bonds because the hydrogens are the same on the outside of either of them. And so letter A says in the C6H6 molecule, all the bonds between the carbon atoms have the same length. They're challenging your understanding of resonance because remember we said on this note, all bonds are considered to be the same length in resonance, no matter if they're double or triple. And so that would be the correct option for this question. So the other topic that goes along with resonance is this concept of formal charge. And formal charge is a little tricky. So there are lots of ways that we can draw certain structures, especially the ones that are resonance structures. There's lots of ways we can draw them. And so formal charge determines which way is most likely. It is a hypothetical charge. These are not true charges we're putting on them. And we're just treating it like everything had the same electronegativity, but we know that's not true. This is just a way that scientists use to figure out what's the most likely structure that's going to form. Overall, the charges need to end up being 0 for a neutral molecule or the ion charge for a polyatomic ion. I give you guys a couple equations for this. So what you're going to do is you're going to figure out how many valence electrons should it have, just if it's normal, just the normal element, minus how many electrons it has in that structure. And then you add up all of those numbers together to figure out what the formal charge is on that ion. Again, it is not a true charge. It is not going to be something that is true. It's just hypothetical. It's just a way scientists have figured out how to make it work the best. So the best possible formal charges is that you want to have your elements to end up being as close to 0. And if you have any negative charges, then it should be on your most electronegative element. So let's review electronegativity again. Remember, with electronegativity, the trend is increase up, increase across. And so you're going to choose whichever, if you have to put a negative on something, it needs to be on one of these elements on the top right of the periodic table. So let's go through and do several of these problems. So you'll notice here on this one, I said each element gets half the bonded electrons, but all the other allocated electrons. Let me explain what I'm saying there. So I left these with dots on it because it's a little bit easier when you're doing formal charges to see all of the dots. And so what we're looking at, what I mean by each element gets half of the bonded electrons. So this is another one that you will sometimes see. This is the equation I think that AP gives you. I didn't love that equation, so you have two different options to look at. This one is the number of non-bonding electrons plus half of the bonding electrons. I just thought that was sort of weird. So I just do half of these dots. Hydrogen should have one valence electron. So based on my equation here, I want to figure out how many does it have minus how many it actually has. That's what this equation is telling us. So hydrogen should only have one. And right now it only has one because we take half of the bonded elements. And so for hydrogen, I have 1 minus 1. So right now, hydrogen is 0. Let's go up here to oxygen. Oxygen should have 6 electrons, but right now it has 1, 2, 3, 4, 5, 6. Remember, we count all the ones that are not bonded are considered a whole electron, only half of the bonding electrons. So 1, 2, 3, 4, 5, 6, 7. So right now we have that oxygen is a negative 1. Carbon should have 4 electrons, and right now it has 1, 2, 3, 4, because remember it gets half of its bonded atoms, and all of them are bonded right now. So 4 minus 4 gives me 0. This oxygen has 1, 2, it should have 6, remember, and it has 1, 2, 3, 4, 5. So that one comes out to a positive 1, if I could write the right number. And then my last hydrogen has just 1. It should have just 1, and so it is 0. If I look at the overall charges, -1, +1 gives me 0. So overall, the charge of this atom is 0, which is what we want it to be. Let's compare it to this option. So these are both the same combination of elements, but they are drawn in 2 different Lewis structures. We're trying to decide which Lewis structure is the best. That is the whole point of formal charge. There's lots of ways to draw some of these. We got to figure out which way is the best. Again, hydrogen should have 1. Right now it only has a single bond, so I take half of those. So 1 minus 1 gives me 0. This carbon has 1, 2, 3, 4. Carbon should be, I'll do it down here, 4 minus 4, so it is 0. This oxygen should have 6. Right now it has 1, 2, 3, 4, 5, 6. So overall it is 0. This oxygen should have 6. It has 1, 2, 3, 4, 5, 6. So it's 0. And this hydrogen should have 1. It only has a bond, so we take half of the bonded atom, so it is just 1. So overall, all of these are 0, which means that this structure is the best structure based on formal charge because all of these equal to 0, which is ideally what we want to have. Let's do the next one. In this next one, we're going to do the same exact thing. So hydrogen should be 1. It only has a single bond, so we take half of those, so it is 1 minus 1. This oxygen has 1, 2, 3, 4, 5, 6. It should have 6, so it gives me 0. This oxygen has 1, 2, 3, 4, 5, 6. It should have 6, so it gives me 0. And then this one has 1, so 1 minus 1 gives me 0. I'm going to assume this is my better structure, but let's look at this one and prove that it is. So again, this one only has, I should have 1, I have 1, so it's 0. This one has 1, 2, 3, 4, 5. It should have 6. It has 5, so that gives me a positive 1. This one should have 6, but it has 1, 2, 3, 4, 5, 6, 7. So it's a -1. This one should have 1, and it has 1. So again, +1, -1 do cancel. I end up with overall neutral atom, which I should, but we prefer the ones with the 0. So this one is going to be my better option, as well as this one was my better option. Let's do our last one. It's like a little puzzle. You just look at each element. Hydrogen has 1 bond, so it's going to be 1 minus 1 gives me 0. This hydrogen has 1 bond, so 1 minus 1 gives me 0. This hydrogen, same thing, got 1 minus 1 gives me 0. So these hydrogens we can all figure out that are just 0. Carbon should have 4. It does have 4 because I have 1, 2, 3, 4. So this carbon is going to be 4 minus 4, which gives me 0. This oxygen should be 6, but I have 1, 2, 3, 4, 5, 6. Again, this one we know is going to be 0. This one's going to be 0. Carbon is going to be 1, 2, 3, 4. Oh, I already did that one. No, this is the other carbon. 1, 2, 3, 4. So this one is 4 minus 4, which is 0. And this nitrogen should have 5. I have 1, 2, 3, 4, 5. So it gives me 0. So again, I'm going to assume this one is the better one. Let me clear it out so you can see the next one. I'm going to focus on the central atoms and see what's going on there because we can figure that all these hydrogens, because they only have 1 bond, are all going to be 0. So I'm not going to worry about them this time. So this carbon I have 1, 2, 3, 4, which gives me 0. This oxygen should have 6. It has 1, 2, 3, 4, 5, 6, 7. Gives me a -1. This carbon has 1, 2, 3, 4, so carbon is good also. This nitrogen should be 5, but it has 1, 2, 3, 4. So again, this gives me a -1, +1, which makes it neutral, but this one was all 0, so our options were this one, and this one. Honestly, with formal charge, most of the time, the way that you draw it normally is going to be the best possible way, but there are some weird ones where they end up being a better shape than what we just intuitively think that it should be. So let's look at one more question. So this is how AP would give it to you. Which of the following Lewis structures best represents the bonding in the N2O molecule considering formal charges? Let's go through and do all of them and decide which one's best. So if I look at this first one, I'm going to do my numbers over here on the side because I'm not going to have room above or below. So for this first one, I should have 5. I have 1, 2, 3, 4, 5, 6. So I have a -1 for that part. And this nitrogen, I should have 5. I have 1, 2, 3, 4. So I have a +1. And then this oxygen, I should have 6. I have 1, 2, 3, 4, 5, 6. Okay, same thing with this one. Should be 5. I have 1, 2, 3, 4, 5 because it is a triple bond. So that ends up being 0. This one has 1, 2, 3, 4. Which gives me a -1. And then this oxygen is going to give me 1, 2, 3, 4, 5, 6, 7, which gives me a -1. Oh, this should be a +1. Let's do this one again. So it should be 5. I have 2, 4, 6, 7. It's a -2. I have 1, 2, 3, 4, 5, which gives me 0. And then for oxygen, I have 1, 2, 3, 4, 5, 6. And then my last one, 1, 2, 3, 4, 5, 6, 7 again. 1, 2, 3 around oxygen. It should be 6. And then my nitrogen, I have 5. 1, 2, 3, 4, 5, 6. Okay, so automatically the one I can mark out is this one because none of them are even close to 0. So that's a big mess. So we'll just say no. Let's look at the other ones and talk about the problems. So this one overall ends up being a -2, which is not true because this is a neutral atom. So we can mark that one out because I have -2, 0, 0. This one is -1, +1, which cancels to 0. This one is also -1, +1, which cancels to 0. Then we have to decide which one is better because both of them end up being neutral, which is what we have to have for this atom because it's not polyatomic. And then we have to decide which one is going to be the better option. Remember when we looked at the notes here a minute ago, it said, if I can find it, here's resonance, here's formal charge. It says that any negative formal charge on individual atoms, ideally on the most electronegative atom. So now we're going to look at this and decide which one is the most electronegative atom. So this one is on nitrogen, and then this one is on oxygen. That negative part is. They want that negative to be on the most electronegative element. So again, electronegativity is increase up, increase across. So if we look on our periodic table, the more electronegative element should be oxygen because it is further to the right. Nitrogen is further to the left. And so my best option for this one is B because nitrogen is not the most electronegative. Oxygen is the most electronegative. And so formal charge is just a little puzzle. Like I said, you will not use this for problems unless the question specifically says what is the formal charge or if it's a resonance structure. Otherwise, we just draw the Lewis structure and just do our normal thing like we did in the last lesson. So don't worry about doing formal charge on everything. You will waste your time on that. We just want to do it on the ones that are resonance or specifically ask something about formal charges or what's the best diagram.